Looking at example 3 on section 5.1. So this is a different kind of function that we're asked to find the intervals of increase and decrease. The previous one was a polynomial. Again, polynomials are defined everywhere, so there was no chance that we had a problem with the derivative as far as it not existing. But regardless, what we always want to do first on these types of problems, where you're asked to find increase, decrease, or critical numbers or anything like that, is to take the derivative. So let's use the chain rule here. Put the 2/5 in front, leave the inner function alone, lower that power by 1, so 2/5 minus 1 is negative 3/5, and then we multiply by the derivative of the function that's on the inside, which is 2. So we'll simplify this. We're going to get, we'll multiply the constants together. We're going to get 4 over, that 5 is in the denominator, so is that. So we're going to get 5 times 2x plus 4 to the positive 3/5 power. Okay, now remember that there's two kinds of critical numbers. There's the kind that occurs when the derivative doesn't exist, and then there's the kind that occurs where the derivative is equal to 0. Notice that if we set this equal to 0, what's going to happen? Well, if I do that, if I set this thing equal to 0, notice that if I multiply both sides by the denominator, then that denominator is going to go away. So setting a fractional function like this equal to 0 is just the same thing as just setting the numerator to 0. So if I do that, 4 is never 0, right? So this is telling us that this function, this derivative, is never 0. So there's no places where the derivative is 0. There's no critical numbers of that kind. So basically, there's no solution to this. So there's no critical numbers of the type where the derivative is 0. There's the other kind of critical number, and that's where the derivative doesn't exist. So what you'll notice is that to find the first kind of critical number, you set the numerator to 0, and you solve that. That had no solution here. The other kind is where the derivative doesn't exist. Well, that's where whatever values will make the denominator 0. So really, you can find both kinds of critical numbers by just first setting the numerator to 0, solving, and then if there is a denominator, set it to 0 and solve that, and that will give you the other kind of critical number. So let's do that for the other kind. So if I set this denominator 0, the first thing I can do is divide both sides by 5, and I get this. Now if I want to get rid of that power there, the 3/5 power, the best way to do that is to multiply by, to raise it to the power of the reciprocal of that. That's 5/3. So I'm going to raise both sides to the 5/3 power. The 5/3 and the 3/5 will then cancel, so I'm just left with this. Well, if you raise 0 to any power, you just get 0. So really, that's the equation we end up with. So 2x is equal to minus 5. So x is equal to negative 5/2, which is negative 2.5. So we do have a critical number, and it's the type 2 kind. Remember that when the derivative doesn't exist on the graph of a function, what do you see on the graph of the original function? You see a sharp point. So that's what we should expect to see on the graph there. Now, keeping in mind there is only one critical number here. So on our table, what we're going to see is only two intervals. We're going to go from minus infinity, the domain of this function is all real numbers, up to that one critical number, and then that critical number up to infinity. So we only have, oops, I shouldn't put a u there, we're not doing a domain here, we're just doing a table. So let me get rid of that. Get rid of that. So remember what we want to do is we want to pick test values. I'm going to abbreviate that with TV. We want to think of the sign of the first derivative. Try to block off that other part there. So for our test value first, we can say, well, let's see, minus 2.5, so we can say like minus 3. And then here, remember that I said if 0's on the interval, that's always a good one to choose. So let's come back and look again at the derivative. There it is right there. If I plug in 0, then this is, I think, pretty clearly positive. If I plug in negative 3, we have to be a little careful here. Negative 3 is going to give us minus 6 plus 4. That's a negative number. The power is odd, so if you raise a negative number to an odd power, both the numerator and the denominator of the power are both odd. In particular, the denominator is important as well, because if that were an even power and we had a negative number, it would be totally undefined. You can't take the even root of a negative number. But this is an odd power, so if you plug in a negative number, it remains negative. So this whole thing is going to be negative. So what we have is, I'll try to write conclusion here. So what we have is the derivative of 0 means the function is decreasing. The derivative negative means the function is decreasing. The derivative positive means the function is increasing. So we've pretty much answered the question here. This function is decreasing on the interval from minus infinity up to minus 5 over 2. And then it's increasing on the interval from minus 5 over 2, minus 2.5 up to infinity. So that pretty much answers the question. They also do ask us to graph this thing, so let's go ahead and do that. I need to enter that in my calculator real quick, and then we'll have a graph. So let's take a look at that. We get, make sure my graph is going to be acceptable here. Okay, I have to change my window, I think. Bear with me for 1 second. I got to change my window, and then we'll be okay. Go from okay. So according to my calculator, we get. Remember, something has to be happening at that minus. At that minus 5 over 2 there. What the heck? I think I have this wrong here. Hold on 1 second. Let me just see about my function. Yeah, well, anyway, the graph, from what I see, looks like this. Negative 2.5, roughly, it's doing this. So the function is definitely increasing there, but I don't really see the decrease. So let me see what's the problem here. Make sure I have the right function. I think probably what it's doing, it's too close to the axis for me to see, so I think it's doing that. So again, notice that we have a sharp point on there. That's the characteristic of the derivative not existing, so just be aware of that.